way to talk. I was intending to, in fact I may even have said so much, that talk should be mostly about the 15 theorem, this one mostly about the 290 theorem. But then I decided I don't know very much about the 290 theorem. And also I've seen at least 3 faces who weren't here at lunchtime. And anyway, I can't avoid being a bit repetitive. So I'm not going to try to avoid it terribly much. I will try to be a little bit slicker about parts that are repetitive. So, okay. So it's really hard. Yes, it really is. Not knowing what I sort of must repeat and what
Some of us know nothing.
Sorry?
Some of us know nothing.
Oh, good. Well, the blame can go on you then. That's really great. So that enables me to do my standard thing. You know, I don't approve of this system of pairs of lectures because it's my experience that almost everybody, present company accepted, gives incomprehensible lectures. And I don't like giving incomprehensible lectures, almost as much as I don't like hearing them. I usually sit at the back in this room, and I make sure to bring a pen and some paper and so on. And so I can work on whatever problem I like. And if by any chance the person at the front says something I can understand, I stop doing my other problem and listen. And that's a good way to do it, I think. Okay. So, so if somebody didn't hear anything, somebody doesn't know. Oh yes, well you said you didn't understand whoever said that. You understand nothing.
I said I know nothing, I wasn't
He knows nothing. Okay. I know nothing. Okay, but did you turn up to the lunchtime lecture?
No.
Oh, great! Absolutely great. You're an innocent. Completely virginal. Well, okay, so I'll go really rather quickly over how these theorems developed and what they say. First, there are 2 notions of integrality for quadratic form. In my book with Sloan, I think it is, I say that I've bedeviled this subject since its infancy. People routinely say integral quadratic form, and they don't say which of the 2 notions they're talking about. And that's really rather annoying. Well, if you take the quadratic form x squared plus x y plus y squared, that's actually equal to the following product. You know, I think I'll make it ax squared plus hxy plus by squared. That's equal to this thing, okay? The h over 2, h over 2, x, y. In the sense that if you multiply this product of matrices out, it's a 1-by-1 matrix whose entry is precisely this thing. And if we didn't suppose that x and y commuted, then we could transfer something between this and this. This is the coefficient of x times y, this is the coefficient of y times x. that xy equals y times x, so we can always choose a symmetric matrix, but only at the cost of making that matrix have non-integers, where I'm supposing that A, B, and H, very neatly there, A, B, and H, I forgot what I'm supposed to make. Yes, but anyway, yes, A, B, and H are integers. So, this quadratic form here is integer valued, but its matrix might not be an integer matrix. So the two notions, I've used the terms just now, the two notions of integral are integer valued, which is if A, B, and H are integers, and integer matrix, which is if A, B, and H over 2 are integers. Of the two famous masters of this theory, Legendre preferred integer valued quadratic forms, and the great Gauss preferred integer matrix quadratic forms. They arise, for instance, in topology quite often. There's some invariant or other, which comes from a quadratic form, and topologists quite often find that they want the integer matrix definition. Anyway, so for these two notions of integer quadratic form, there is a constant, for either of these notions, there is a constant which I'll call C, such that I need to define the notion of a universal quadratic form. The subject started in 1770 when Lagrange proved that the four squares theorem, every positive integer is a sum of four squares. So that says that the quadratic form x squared plus y squared plus z squared plus t squared. T is the letter coming after z. Because if t isn't present, it's very convenient to use x, y, and z. Anyway, this quadratic form represents every positive integer. Every positive integer is a sum of four squares. We nowadays phrase it as saying that this quadratic form, which is a four-variable quadratic form, is universal. What do we need to know to find that a quadratic form is universal? That's the subject matter. In the lecture course that I gave, I think in 1993 on quadratic forms, I quoted some then recent theorems of Lagrange's below to prove or to deduce that whichever notion of integral you prefer, there's a constant C, such that you only have to check up to that constant. And if all numbers up to that constant are represented, then all numbers are represented. The constant for integer matrix quadratic forms turned out to be 15, and the constant for integer value quadratic forms turned out to be 290. So we have the 15 theorem and the 290 theorem. I may say that I suppose I may say anything. I've forgotten what I may say. I can forget tremendously quickly nowadays, even without trying. Never mind, it'll probably come back to me and look at something else. I didn't regard, yes, this is not the thing that I may say, it. This is twice I've forgotten inside a period of about 3 seconds. Yes. a three-variable quadratic form cannot possibly be universal. That's a wonderful theorem, and I may sort of explain just why later on, but let's take it as an axiom. It was well known to people quite a long time ago. And so the first possible candidates for universality are four-variable quadratic forms. And in the history of the subject, the idea is gradually... Sorry? Oh, yes. Oh, by the way, I meant to say something, but I don't want to say just at this instant, about indefinite quadratic forms. Namely, there is no theory. And I can tell you why sometime. Yes, so the possibilities for universality start at 4 dimensions, 4 variables. And the question, as it was always considered, until I had this brilliant idea of considering a different question, is which, can we enumerate all the 4 variable quadratic forms? Ramanujan really started work, the 20th century work on that. There was a little bit of stuff about individual quadratic forms, starting with Lagrange's 4 squared theorem, for instance. But for instance, it was also known that x squared plus y squared plus c squared plus 2t squared was universal, and so on. But Ramanujan tried to enumerate the diagonal forms. That's just ax squared, by squared, cz squared, dt squared, some of all those things. And he wrote down a list of 55 of these things. The astonishing thing is that he made a mistake, and even more astonishing, what the mistake was, that this particular mathematician should make this particular mistake is amazing. Namely, he listed the form 1255 as being a universal quadratic form. That's x squared plus 2y squared plus 5z squared, 5t squared. And it isn't. It fails to represent 15. Ramanujan could miss that off, and this particular person could make that particular mistake. I find amazing. I call it Ramanujan's renegade form. It does, in fact, represent every number except 15. I used it quite some time ago to prove a neat little theorem that if a quadratic form represents every number less than 15, then it automatically represents every number greater than 15. Anyway, that's a shock. And in a sense, but it's a rather weak sense, the Ramanujan renegade form is the only number that manages to meet this 15. Okay, well, I was giving this lecture course on quadratic forms, postgraduate lecture course on quadratic forms, which was, I think, in this room. I must have thought it was in this room, although the number of students at it was 6, maybe 8 or something, or maybe it was downstairs in 240. And in the next to last lecture of that course, I quoted some theorem. I've been saying theorems, but it's really just a theorem that implied that, I quoted it to deduce, the deduction was trivial, by the way, that there was a number C for any particular one of the 2 definitions of integral, such that you only had to check up to the constant C. Those 2 numbers I call little c and big C. Little c was the one for integer matrix forms, which turned out to be 15 when we did it, and big C turned out to be 290. Then I was dashing away immediately after to a conference in Boston. No, I got there. In the next to last lecture. And in the last lecture, I wrote a theorem: if a positive definite integral matrix quadratic form represents the numbers ... so I drew a dotted line to be filled in, then it is universal. And I'm going fairly quickly now. The number 1 has to be on the dotted line, because otherwise, well, never mind, it has to be on the dotted line. And then the form x squared represents 1, but it doesn't represent 2. 2 isn't a perfect square. So the number 2 has to be on the dotted line. The form x squared plus y squared represents 1 and 2, but it doesn't represent 3. 3 is not a sum of 2 squares. So the number 3 has to be on the dotted line. The number 4 does not, because if we demanded that our form represent 1 as a certain vector, then at twice that vector it represents 4. The number 5 does have to be on the dotted line. You just write x squared plus 2y squared. Number 6 has to be on the dotted line. Number 7 has to be on the dotted line. X squared plus y squared plus z squared represents 1 to 6, but not 7. Number 8 doesn't, you, so to speak, double the vector that represents 2. 9 doesn't, treble the vector that represents 1. 10 does, it turns out. 11 doesn't, for a rather more subtle reason than the type of reason we've discussed before. 14 and 15 do, 13 doesn't. And then we, in class, discussed the forms that represent those 9 numbers, which are 1, 2, 3, 5, 6, 7, 10, 14, 15. And we showed that the form that represents those represents every number up to about 50, which was already a pretty good hint. And then Chris Simons ran out of the room to the little console room there. Will got excited, by the way. He programmed a machine and discovered that if a quadratic form represents those 9 numbers, then it represents every number up to 30,000. That made it obvious that little c was going to be 30,000. Sorry, it was going to be the 50. Next day, I flew off. No, I didn't fly off. I got a train.
You made this mistake at noon also.
Sorry?
First time at noon also. You first time you took the plane.
Anyway, I went to this conference in Boston, which I think was on the monster group, which I was very interested in at the time. And however, I didn't learn much from the other talks on that, because I sat in the back thinking about what became the 15 theorem. I wouldn't have gained all that much anyway, because I knew more about the monster than the people giving the lecture. But never mind that. While I was there, I did the thing that I was describing at lunchtime, which was reducing the problem to showing that about 200 particular quadratic forms in 4 variables were all universal. Then I started dealing with those forms as well, continued dealing with them when I got back to Princeton. Reduced 200 to 9 pretty quickly, then to 7, and then the thing that reduced 7 to 6 actually reduced 7 to 2. It's applied to quite a few examples all at once. And then for the last 2, one of the students who attended the course, Will Schneeberger, provided some valuable help. And in the end, we polished those 2 recalcitrant forms off. I can't now remember exactly which two they were. So eventually we had proved the 15th theorem.
So, one question. You those are ineffective, which was the issue.
No, the point is it was effective, the theorem that was quoted. It was that,
I'm asking why, I mean, you knew there was a C
yes.
immediately. Was that
Yes.
number bigger than your 30,000? I think it's ineffective. At least that's what I meant.
I remember it as being effective, but it doesn't actually make any difference from the point of view of the existence theorem. That's what I just said.
No.
So we don't need to argue about it. But, anyway, okay, we came back, and within a week or so, had finished off the 15th. Then I gave Manjul the problem of proving the 290 thing. And I told him the methods that have been used for the 15th thing. Well, not that. I mean, Manjul was, and I learned it was now John Hanke also, was one of the few people who must have read my books on the subject, one of which was written slow, which contains a description of a symbol that represents the genus of the quadratic form. And that sort of makes it much, much easier to think of than with Hanke. Traditionally, I wonder whether to say things about the genus now. I suppose I can. It's always dangerous to totally change your mind about the way you about an actual instance. The genus of quadratic form. The way it's traditionally described is using the periodic numbers. The way periodic numbers are traditionally defined is in terms of various completions of the rational numbers. I really prefer the logical way of defining the periodic numbers, which is this. Let's think of specifying a number, an integer, let's say. Well, you can get a bit closer to specifying that number if you say what it is modulo p. You get closer still if you say what it is modulo p squared. You've thinned out the integers satisfied by a factor of p. And modulo p cubed, of course, when you say what it is mod p squared, you better make sure that that's consistent with your decision of what it was modulo p. Okay, now you're ready for the definition of a p-adic integer. A p-adic integer is the simultaneous, well, let me just say, it is a set of congruencies modulo all powers of p that are consistent. Mutually consistent. Does everybody get that yet? Sorry? What did you say?
That's a standard definition.
It's good
V mod p to the n. A
Well,
protected limit.
Yeah, you just specify your integer modulo p to the n for all n in such a way that the specifications modulo 2 powers of p are mutually consistent. And then what you've specified is a p-adic integer. One doesn't need to say all this nonsense, which is not nonsense, of course, about Cauchy sequences and completions and all that sort of stuff. The logical definition captures exactly what you need and no more, which I think is a very nice way of doing things. Okay. Now, there is, however, another completion of integrals, which is a much more famous one. The standard, the rationals, the one that completes to the reals. And conventionally, that's sort of referred to sometimes as the infinity-added completion, which is very, very silly. Everybody thinks I'm silly because I insist on talking about the prime minus 1. But I'm not silly. I assure you, of course, it's a silly person, wasn't it? I assure you. I want to remark, when you talk about factorizations of the integers, or non-zero integer, a factorization is minus 1 to the something, let's call it alpha, 2 to the beta, 3 to the gamma, and so on, where only a finite number of these powers of primes, I want to call minus 1 a prime, so I'm going to, only a finite number of these prime powers are different from 1. Okay. And you might notice that minus 1 is a slightly unusual prime, in that it only has 2 powers, namely 1 and minus 1, whereas all the others have infinitely many distinct powers. Nevertheless, I propose to call minus 1 a prime. And I might say that if one looks back historically to the first use of these p-adic numbers and so on, the primes like this minus 1 are called unit primes, not infinite primes. It's a very natural definition. I remember when John Hanke came recently to give a talk. I was occupied in talking to him for about half an hour, and he was remarking about this being a sensible definition for these purposes. As I said, it's a sensible definition for every purpose. When one's discussing quadratic forms, all of these primes behave in a very similar way. This prime behaves in a more complicated way, and this prime behaves in a less complicated way. And it's very interesting. I want to illustrate that a little bit. If one considers which numbers are squares. Now, if one considers the p-adic numbers modulo p-adic squares, then for p, let me call this the square class problem. For b greater than or equal to 3, the square classes are, I will call u plus, u minus, pu plus, and pu minus, where u plus and u minus are p-adic units, they're not divisible by p. And they're represented by 1, or any other quadratic residue modulo p, and any non-residue non-quadratic residue. There are 4 square classes for p greater than or equal to 3. For p equal to minus 1, there's just u and pu, where u means a number not divisible by minus 1. What does that mean? Every number appears to be divisible by minus 1, but not if you think of the factorization I was mentioning to you. Not divisible by minus 1 means it's positive. Okay? The power of minus 1 is plus 1. So let me call that PU plus, sorry, U plus and PU plus. So there are only two square classes. For B equal to 2, what are the square classes? They are U1, U3, U5, and U7. And 2U1, which of course I could call PU1, 2U3, 2U5, I'm sorry, I'm having difficulty controlling my hand, and 2U7, where U3, for instance, means something in the form 8n plus 3. Every square of a number prime to 2 is congruent to 1 modulo 8. And so the residue class modulo 8 is an invariant modular multiplication by quadratic squares. And also whether you've got an odd power of 2 or an even power of 2 is an invariant. So for 2, there are 8 square classes, which means there's considerable complication of 2. For minus 1, there's only 2 square classes, which means the simplification for minus 1. When one talks about quadratic reciprocity, which is a subject that arises a lot in discussion of quadratic and elsewhere, the usual statement of quadratic reciprocity mentions only odd positive primes. In other words, it does not mention minus 1 as a prime. However, it turns out that minus 1 can be included free of charge. The usual definition has accompanying it some little statements called accompaniments to quadratic reciprocity. But the minus 1 case of those accompaniments is just a particular case. In other words, what's the statement say? Is if I've got 2 distinct odd primes, P and Q, then whether P is a square modulo Q and Q is a square modulo P, those are 2 related things. The answers are the same unless both P and Q are minus 1 mod 4. That statement usually is excluding minus 1 by definition or fiat or something, but it includes minus 1. It's helpful. The statement, the accompaniment for 2 is really rather different. Anyway, that's that. Sorry, I'm getting a bit lost in the words.
Genius.
Okay, I was just going into the hobby horse, but then I'll now get off and do stop rocking. Right. Well, I suppose I have to discuss again the notion of escalation. For the easy notion of integrality, matrix integrality, the off-diagonal entries in a matrix represent inner products as distinct to norms. And so to say that something is matrix integral is effectively saying that you can use it. Sorry, perhaps I'd better talk about what a positive definite quadratic form does, so to speak. A positive definite quadratic form is equivalent over the reals to the sum of squares form, and therefore one consider its values as being the values of, as defining an inner product on a certain space, on the quadratic form space, making it into a Euclidean space. And you've just done a base change to make that happen. And so the vectors that were integral in your original coordinate system now form a lattice. The sum of 2 of them is a number. And when you multiply any one of them by an integer, you get another. An instrument might be negative, for instance. So we've got the notion of lattice, and the experts hardly distinguish between a positive definite quadratic form and a lattice. They hardly distinguish between an indefinite form and a lattice too. Then it's a lattice in a non-Euclidean space. So let's be experts, and let's think of our quadratic form as a lattice. And then our lattice, I'm just wondering which way to go. I think I can go a little bit quicker than I was just about to. Well, I'll go back to going a little bit slower than I was just about to. There is some vector in our lattice where it represents 1. Then there is another vector where it represents 2. And now there's a little number a here, which is the inner product of the vectors e1 and e2, which I've just defined, essentially, I've just spoken of. And we know about a, that a squared is less than or equal to 1 times 2. That's Cauchy's inequality. 1 is e1 dot e1, 2 is e2 dot e2, and a is e1 dot e2. So this is Cauchy's inequality. The square of e1 dot e2 is less than or equal to e1 dot e1 times e2 dot e2. So a squared is less than or equal to 2, which means a is 0 or 1, or maybe minus 1. But if it's minus 1, I can change the sign of the vector that I was going to call e2. Well, let's do a tricky one. Change the sign of it, which changes the sign of the top row and the first column. That will change the value of a. So I might as well suppose that a is 0 or plus 1. Okay. And now, this form, so if a is 0, we get the quadratic form with matrix diag 1 and 2. If a is 1, then I can subtract e1 from e2, which does that. This is e2 minus e1 now. And then, at the moment, I've done it with respect to our hybrid, a pair of bases. E1, the old base, E1 and E2, and the new base up here, the new base labels column. But I'm now going to change this E2 to E2 minus E1. And that boils down to subtracting the leading sorry, that was the 1 here. And I now get this. So, what I've done is one stage in what we call the escalation procedure. The quadratic form contains the 1 by 1 quadratic form x squared, and it represents 2. Then it contains either x squared plus 2y squared, which is the first case I did, or the second case, which simplifies to x squared plus y squared. That's the escalation procedure. Well, let me define it more precisely. If I have found inside my unknown quadratic form an n-dimensional quadratic form, and it doesn't yet represent all numbers, that n-dimensional quadratic form, then there's a first number, the first positive integer that it doesn't represent. Let's add a new vector to the n-dimensional sublattice we have at the moment. Add a new vector which it represents this first missing number, and then simplify. When we add a new vector, let me discuss the case. I think I'll discuss the easiest case. When we've got this two-dimensional lattice here. Which supports the quadratic form x squared plus y squared. What's the first missing number of x squared plus y squared? Well, the answer is 3. So we choose an E3, which I'm going to change in a moment, at which the vector, the value of the form is 3. And then we fill in two integers here, which are the inner product of this E3 with E1 and E2 respectively. And then, what are there? There are various limitations on them. The limitation I've already used is the quotient inequality, which in this case says that a squared is less than or equal to 1 times 3. Very similar thing though says that b squared is less than or equal to 1 times 3. So a squared and b squared are at most, they're at most 1 in size. And moreover, we can suppose they're positive by this sign change, or non-negative, we should say. And so they're both 0 and 1. So that's, so if one of them is a 0, then we're reducing this quadratic form. If the other one is 0, it's reduced already. Otherwise it's 1, and then I subtract the first column from the second column, then subtract the first row from the second row. I didn't subtract both entries when I did the column thing, and it reduces to this 1, 2 thing. And if they're both 1, subtract this first column from the last column, these are 1s. Never mind. It simplifies. So what happens is, I was busy saying somewhere how the escalation goes. It goes from the 0-dimensional form, which is useful in this theory, which has determinant 1 and dimension 0, to the 1-dimensional form, because 1 is the first number that's missing, which has determinant 1 and dimension 1. The first number missing was this 1 here. The first number missing here is 2. That permits two different possibilities. This is determinant 2 and dimension 2. This is determinant 1 and dimension 2. And then there are 9 forms here, ranging, from diag 1, 1, 1 to diag 1, 2, 5. They are all of dimension 3, of course, so this is little subscript 3, and the determinants go from 1 to 10. However, 5 is missing, so there are only 9 of them. That's the escalation procedure, which I hope you can understand from this quick survey. And then we get a total of 204 forms here. The total number here was 1, here it's 1, here it's 2, here it's 9, and over here it's 204. And if we can prove, which we could, that all of those 204 forms is universal, we don't need to do anymore. Because at least one of these forms is contained in the form that we're given. That's the work that I did together with some little help from Schneeberger of the day, so to speak. Okay. But now, how does one prove that a quadratic form is universal? How, for instance, did Lagrange prove that its 4 squares form was universal? Well, now the last question is not so terribly good, because there's a more powerful theorem than Lagrange's 4 squares theorem, which is Legendre's 1798 3 squares theorem. And that says that an integer is not the sum of 3 squares. Let me try and think whether it's counterpositive or not. An integer is the sum of 3 squares. It is the sum of 3 squares, unless, as long as it is positive and not congruent, and not of the form, power of 4 times the number of the form 8n minus 1. And where do those two conditions come from? Well, the positive condition is that it can't be a sum of 3 squares over the integers if it's not a sum of 3 squares over the reals. So there's one lovely field, that ring, that includes the rationals and the integers. It's got to be a sum of 3 squares over the reals, which denotes it to be positive. And then the other demand, it must not be a power of 4 times 8n plus 7, or 8n minus 1, if you like. That's because those numbers are not sums of 3 squares over the 2 adic integers, or even the 2 adic rationals. And that's easy to prove. What's a square in the p-adic numbers, in the 2 adic numbers? It is an 8n plus 1 number, or a power of 4 times 8n plus 1 number. It's p prime part, so it's got to be a square, which is the 8n plus 1 number. And look, so it's necessary 0, 1, or 4. This is a square. It's 0, 1, or 4 modulo 8. So, not right, because I think this is what x squared is. This is what y squared is. This is what z squared is. Modulo 8 in each case. There's no way of getting 7 by adding these numbers. Okay? So 8n plus 7 isn't a sum of 3 squares. And now, how about an even number being a sum of 3 squares? Well, it would have to be either all squares of even numbers. In that case, we can divide by 4, iterate again, or else 2 1s under something, 2 1s and a 0 or 4. And I just lost it. Oh, there's just a trivial point in this. It only thinks that the sums of 3 squares in the 2 adic are powers of 4 times 8n plus everything except 7. Okay, so right now that's the powers of 4 times the 8n plus 7s are really rather a lot of integers. Most integers are sums of these squares. So let's discuss how to prove the four-square theorem. I've now got a quadratic form that looks like this, and then it has the number n here at the bottom. And n, remember, is the first number that's missed by this quadratic form. So it's sort of a 7 here when we start off, but that's before we do this reduction. When we do the reduction, which amounts to subtracting multiples of the first, second, and third columns, these numbers get smaller. And same for here, and this number becomes some number less than or equal to 7. And so the quadratic form 1, 1, 1, diag 1, 1, 1, escalates to the quadratic form diag 1, 1, 1, something less than or equal to 7, which I'll call n. Now I'm going to prove, so how many of those are there? The answer is 7 of them, n equals 1 to 7. Let's prove that they're all universal. Okay. So let n be the first number not represented by 1n. I didn't mean n up here. Oh yes, no, that's all right. Big N be the first number not represented by this. Then, where are we? For m, remember m was less than or equal to 7. For n equals 1, 2, 3, 4, 5, 6, 7. N minus n, r, is congruent to r. Well then, I suppose, then if n is congruent to 0 mod 8, n minus n is congruent to 7, 6, 5, 4, 3, 2, 1. All congruences will be mod 8. Okay, but n minus n, okay, what am I trying to say? I didn't mean n minus n, I meant, oh, yes, it's, oh yes, no, I did mean n minus n. N minus n is this. So in these cases, and I've checked this to say done, because in these cases this number, n minus n, cannot be a power of 4 times 8n plus 7, 8k plus 7. So there's no more to check here. If n is, if n minus n is represented by the 3 square form, then n is represented by the 4 square form. Take the last variable t to 1. Okay. So what do we do now? If I'm going to do n minus 4n here, n is 1, n minus 4n is 5 in this case. So that's good, because if n is, if if n minus 4m is represented by the 3 square form, then again n is represented by the 4 square form. You just take t equals 2. Now we don't need to worry about these. That's not a very good one. Oh yes, I know what we do now. In this case, if n yes, I have to do a slightly different thing. If n is, if m is 4 to the r, or 4 to the 2r, now 4 to the 2r plus 1, 4 to the r, that's like this as well. The only case we haven't dealt with is when n is an odd power of 4. That's the only thing we can make it be in this continuous class. Then what we do is we take 4 to, let me call it 4 to the 2 plus 1. Then we take n minus 4 to the 2r. And that works. I hope you've seen what I'm doing. I'm just representing a number slightly smaller than n minus a certain, m times a certain square, by the 3 square form. And that becomes obvious then that n itself is represented by the 4 square form. So what we're doing really is we're saying that by the Legrange's theorem, the 3 square form represents an awful lot of numbers. And we only have to tinker a tiny little bit with our first number not represented to get a representable number that's m times the square. It differs from the given one by being m times the square less that is. Okay. So Legrange's theorem was generalized really by Gauss. I mean, he generalized it a few times by himself, so to speak, or by himself. But then Gauss, as usual, wiped the floor with anything as his predecessors had done. And I don't quite know the history that I'm confidently asserting here, but it's roughly like this. What makes Legrange's theorem work is that the 3 squares form is unique in its genus. The genus means, well, 2 forms are in the same genus if they are equivalent p-adically for every p, including minus 1. When you include minus 1, that means they're equivalent over the roots. That's the one place where one has to say something really different about minus 1 than for the other p. Because it's easier rather than harder. What does one do? The great theorem about representations is that well, it's really equivalence of quadratic forms. It is about equivalence, but I'll state it in terms of representations anyway. That if a number is represented p-adically, no? Yes, if a number is represented p-adically by a form, for all p, including minus 1, then it's represented by some form in the same genus as the given one. And this notion of a genus is very nice in that the number of genera is a class, the number of classes in a given genus, is finite. And it's quite easy to work out when you've got names for different genera. Genera is the form of genus, And every now and then it's 1. And Legendre's theory works for the free squares thing because that is unique in its genus.
Very rarely.
Sorry?
Very rarely is it one.
Yes, I said every now and then, I think. I'm not implying it's a frequent, but at the beginning it's fairly frequent. And of the 9 forms in 3 dimensions that we reached by the escalation procedure, all but one of them is unique in its genus. That's a very nice thing. And when the form is unique in its genus, one gets that a number that's represented p-adically for all p by a given form is actually represented by the form. Okay. And then when that happens, one's got a good handle. The one case that it doesn't happen for is this form, which before I called 7 sub 3, a 3-dimensional form determinant 7. This is p-adically, this is in the same genus as diag 1, 1, 7. But it's not actually equivalent to that form. These two constitute a genus. And then instead of a Legendre-like theorem, one gets a different theorem. From a representation theoretic point of view, you can't pull these apart. You can tell if a number is p-adically represented by one of these forms, then you can tell that it's p-adically represented by the other one too. But it might not actually be represented. The numbers that are represented by the genus, that means represented by either this form, let's call this F, or this form G. You can tell what that class of numbers is congruentially, but you can't tell which is which. It's a very funny situation. That's what I call you can't pull the genus apart. Given congruential information about the number you want, oh, it's not enough. That's enough to tell that it's represented either by F or by G. A very curious situation. So what does one do with this form, or rather with this 4-dimensional forms that this escalates to? Well, when this escalates to quite a few forms. I don't know how many. Remember that there are 204 forms altogether. You get in the escalation. This probably escalates to a dozen forms. For some of those, it might happen that both F and G arise as sections of the 4-dimensional form. Okay? In that case, they're done. You know that that for a given number, you know when a number is congruentially represented. It's congruentially represented either by F or by G, but it doesn't matter because they're both sections of the given form. So that's one of the easy cases. I mean, the easiest cases. I don't know who that was. It says 2 missed calls. I didn't hear it going before. So, anyway, various things happen. There can be as many as 4 forms in the genus of one of these 3-dimensional forms. What does one do in a case like this? It's very unlikely that all 4 forms arise as sections of the 4-dimensional theory. Well, you do different things. We employ arithmetical tricks. Sometimes you can prove that if, let's go back to the sort of example where there are 2 forms of the given genus. You can prove, you suppose that a number is represented by G instead of F, the one you wanted. But then it must be, say, even, and then you do something else and you fiddle around for a time, and then eventually you find that it is represented by this from a whole number of tricks. As I say, I reduced the set of 204 forms. I never actually counted them. I think I first learned that the total number of such forms was 204 from Manjul as a week ago. I developed arguments quite often dealt with a whole lot of forms at once, because 1, 1, 1, n was dealing with 7 forms at once. So I didn't need to count the individual forms. But anyway, well, the arithmetic, combinatorial, geometrical tricks. And eventually I managed to get rid of, well, I must give Schneeberger his due. He helped me with the last two. Managed to get rid of all of them, and so proved the 15th theorem. With the 290 theorem, oh, perhaps before I leave the 15th, I think I'll do it in this order. With the 290 theorem, the problem is much harder. There's 6,436 forms that you reach in 4 dimensions by the escalation procedure. They aren't actually all universal, but roughly the method is the same. We try to prove them all universal. It's much harder to prove 6,000 forms universal. It's much harder to prove that each of the individual forms is universal. It's made more hard by the fact that you've got 6,000 to do. Well, I taught Manjul everything I knew, and he managed to get rid of about 700 of these forms. And I kept on asking him every now and then, have you made any progress with the 290? And he would report back something or other. But then he said one time he was interested in John Hanke in this problem, and Hanke had essentially applied the analytic method. I said something wrong, I think at lunchtime, I'm not quite sure. But anyway, Hanke, Manjul got everything that could be got out of these arithmetic tricks that had been sufficed completely from the 15th problem. And it didn't suffice. All it did was get rid of 700 and something forms out of 6,000. Hanke applied the analytic method, which we always knew should be applied, but I was always afraid of applying it because it gives large numbers. Well, Hanke wasn't so much afraid of the large numbers. He did the analysis when the arithmetic thing came, and then he also did the computation, as far as I understand, to prove that the analysis just tells you that sufficiently large numbers are represented, but a number can be insufficiently large for the analysis and yet very large. And so eventually computation was resorted to, the massive computation and a massive piece of analysis. And so we have the 290 theorem. Bhargava and Hanke got a prize for that from the AMS. Now, what can I say about Manjul's fields matter? Well, I can't really say very much. This was not a large part of it. Don't let me give anybody that impression by accident. It's what made me think of these theorems again, having not thought of them for 20 years. But it's not a large part of what Manjul did in his fields, because it was large enough to be mentioned in the citation. And so that's that. I'm still very proud, I must say, of having thought of expressing the problem in this way. Everybody else, when they were talking about universal forms, were trying to list all the 4 variable universal forms. Isn't it much easier to say, let's say in the integer matrix case, all you have to do is check 1 to 15. Well, it is easy. You don't even have to check all those. Just let me show you. Let me write it down. Sorry? Relative. Oh, sorry. Oh, yes, I'm 15 minutes over. Well, let me not do it.
I mean, maybe somebody they want to go.
Yeah, no, sorry. I thought I was finishing at 6, so I was looking at my watch by that, thinking, my God, I've got to go on talking. Very, very happy not to. Let me stop talking.
Yeah, that's how.
Yeah, very sure. The C theorem, do you believe it could be generalized as a bounded height condition that if the quadratic form over ring of integers of the number 2?
You're going to talk about some other number fields. I don't really know much about those.
Do you have philosophical reason why a C theorem should be true? Because you knew it already from the results you mentioned. If you didn't know, would you expect it to be true?
I'm not at all sure. I think it would be my expectation that I would be terribly hesitant about it. I could imagine the following. You demand that one shows something. Then you demand 2, 3, 4. And then you find you've represented everything up to 10. And then you still find you have to say that 17 must be represented. So you represent that. And then you find everything up to 55 is represented, and you've got to get that. I don't see why that shouldn't happen.
No, because over C you have an order, but over other ring of integers you don't have it.
Yeah.
Question of representation.
I remember talking about this sort of thing before the big what I'm saying, people's hours in this one, so much it's funny, I don't speak about, sorry, you want to just formally let everybody go.
Yeah, okay.
Goodbye.